Hello friends, in this second part of Einstein's relativity discussion, we shall be talking about relativity of length, the Lorentz transformation and Doppler effect for light. The relativity of length. If you want to measure the length of a rod that is at rest with respect to you, you note the positions of its endpoints on a long stationary scale and subtract one reading from the other. If the rod is moving, however, you must note the positions of the endpoints simultaneously, or your measurement cannot be called a length. Figure here suggests the difficulty of trying to measure the length of a moving penguin by locating its front and back at different times. Because simultaneity is relative and it enters into length measurements, length should also be a relative quantity. The measured distance between 2 points in space also depends on the frame of reference of the observer. As with the proper time interval, it is very important in relativistic calculations to correctly identify the observer who measures the proper length. The proper length between 2 points in space is always the length measured by an observer at rest with respect to the points. Often, the proper time interval and the proper length are not measured by the same observer. The length of an object measured by someone in a reference frame that is moving with respect to the object is always less than the proper length. This effect is known as length contraction. But here we need to be careful. Length contraction occurs only along the direction of relative motion. Also, the length that is measured does not have to be that of an object like a rod or a circle. Instead, it can be the length or distance between two objects in the same rest frame. For example, the sun and a nearby star, which are at least approximately at rest relative to each other. Now, the question is, does a moving object really shrink? Reality is based on observations and measurements. If the results are always consistent and if no error can be determined, then what is observed and measured is real. In that sense, the object really does shrink. However, a more precise statement is that the object is really measured to shrink. Motion affects that measurement and thus reality. When you measure a contracted length for, say, a rod, you do not locate the two ends of the rod simultaneously. You first located the rod's front end and then slightly later its rear end, and that is why you measured a length that is less than the proper length. The Lorentz transformation equations. Suppose two events occur at a point P and Q and are reported by two observers, one at rest in a frame S and another in a frame S prime, that is moving to the right with speed v as shown in figure. The observer in S reports the events with space-time coordinates x, y, z, t, and the observer in S prime reports the same events using the coordinates x prime, y prime, z prime and t prime. According to Galilean relativity and the equations, the distance between the 2 points in space at which the events occur does not depend on motion of the observer, that is, delta x is equal to delta x prime. Because this prediction is contradictory to the notion of length contraction, the Galilean transformation is not valid when v approaches the speed of light. So, here we present the correct transformation equations that apply for all speeds in the range where v lies between 0 and c. The equations that are valid for all speeds and that enable us to transform coordinates from s to s prime are the Lorentz transformation equations. X prime is equal to gamma into x minus Vt, y prime is equal to y, z prime is equal to z, and t prime is equal to gamma into t minus v upon c square into x. These transformation equations were developed by Hendrik A. Lorentz in connection with electromagnetism. It was Einstein, however, who recognized their physical significance and took the bold step of interpreting them within the framework of the special theory of relativity. Notice the difference between the Galilean and Lorentz time equations. In the Galilean case, t prime is equal to t. In the Lorentz case, however, the value for t prime assigned to an event by an observer O prime in S prime frame in figure depends both on the time t and on the coordinate x as measured by an observer O in the S frame, which is consistent with the notion that an event is characterized by 4 space-time coordinates, that is x, y, z and t. In other words, in relativity, space and time are not separate concepts, but rather a closely interwoven with each other. If you wish to transform coordinates in the S prime frame to coordinates in the S frame, simply replace v by minus v and interchange the primed and unprimed coordinates in above equations as shown here. When v is very less than c, the Lorentz transformation equations should reduce to Galilean equations. As v approaches 0, v upon c is very less than 1. Therefore, gamma approaches 1 and the Lorentz transformation equations indeed reduce to the Galilean space-time transformation equations. In many situations, we would like to know the difference in coordinates between two events or the time interval between two events as seen by observer O and O prime. So, we can express the difference between the 4 variables x, x prime, t and t prime in the form as delta x prime is equal to gamma into delta x minus v delta t and delta t prime is equal to gamma into delta t minus v delta x upon c square. These equations are for converting coordinates from s to s prime. Delta x is equal to gamma into delta x prime plus v delta t prime and delta t is equal to gamma into delta t prime plus v delta x prime upon c square are the equations for converting coordinates from s prime to s. Here delta x prime is equal to x prime 2 minus x prime 1 and delta t prime is equal to t prime 2 minus t prime 1 are the differences measured by the observer O prime and delta x is equal to x 2 minus x 1 and delta t is equal to t 2 minus t 1 are the differences measured by observer O. Here we have not included the expressions for relating the y and z coordinates because they are unaffected by motion along the x direction. The Lorentz velocity transformation equations. Suppose two observers in relative motion with respect to each other are both observing an object's motion. Previously, we defined an event as occurring at an instant of time. Now, let us interpret the event as the object's motion. Here, we wish to use the Lorentz transformation equations to compare the velocities that two observers in different inertial reference frames S and S prime would measure for the same moving particle. Let S prime move with velocity v relative to S. Suppose that the particle moving with constant velocity parallel to x and x prime axis in figure sends out two signals as it moves. Each observer measures the space interval and the time interval between these two events. These four measurements are related by these two equations. Delta x is equal to gamma into delta x prime plus v delta t prime, and delta t is equal to gamma into delta t prime plus v delta x prime upon c square. If we divide the first of these two equations by the second, we find delta x upon delta t is equal to delta x prime plus v delta t divided by delta t prime plus v delta x prime upon c square. Dividing the numerator and denominator of the right side by delta t prime, we find the following equation. Delta x upon delta t is equal to delta x prime over delta t prime plus v whole divided by 1 plus v upon c square into delta x prime upon delta t prime. However, in this differential limit, delta x upon delta t is u, the velocity of the particle as measured in s, and delta x prime over delta t prime is u prime, the velocity of the particle as measured in s prime. Then we finally have u is equal to u prime plus v divided by 1 plus u prime into v divided by c square as the relativistic velocity transformation equation. This equation reduces to the classical or Galilean velocity transformation equation as u is equal to u prime plus v when we apply the formal test of letting c approaching infinity. This result shows that a speed measured by c by an observer in S is also measured as c by an observer in S prime, independent of the relative motion of S and S prime. This conclusion is consistent with Einstein's second postulate: the speed of light must be c relative to all inertial reference frames. Furthermore, we find that the speed of an object can never be measured as larger than c, that is, the speed of light is the ultimate speed. Doppler's effect for light. The Doppler effect is a change in frequency of a wave or other periodic event for an observer moving relative to its source. It is commonly heard when a vehicle sounding a siren or horn approaches, passes, and recedes from an observer. The recede frequency is higher compared to the emitted frequency during the approach. It is identical at the instant of passing by, and it is lower during the recession. The Doppler effect holds not only for sound waves, but also for electromagnetic waves, including microwaves, radio waves, and visible light. For sound waves, the Doppler effect depends on two velocities, namely the velocities of the source and detector with respect to the air. Air is the medium that transmits the waves, but this is not the situation with light waves, for they and other electromagnetic waves require no medium. They are able to travel even through vacuum. The Doppler effect for light waves depends on only one velocity, the relative velocity between source and detector as measured from the reference frame of either. Let f0 represent the proper frequency of the source, that is, the frequency that is measured by an observer in the rest frame of the source. Let f represent the frequency detected by an observer moving with velocity v relative to the rest frame. Then, when the direction of v is directly away from the source, f is equal to f0 under root 1 minus beta upon 1 plus beta. Here beta is equal to v upon c. When the direction of v is directly towards the source, we must change the signs in front of both beta symbols in equation. Low speed Doppler effect. For low speeds, that is when beta is very less than 1, the equation just derived can be expanded in a power series in beta and approximated as f is equal to f0 into 1 minus beta plus half beta square. The corresponding low speed equation for the Doppler effect with sound waves or any wave except light waves has the same first two terms, but a different coefficient in the third term. Thus, the relativistic effect for low speed light sources and detectors shows up only with the beta square term. Astronomical Doppler effect. In astronomical observations of stars, galaxies, and other sources of light, we can determine how fast the sources are moving, either directly away from us or directly towards us, by measuring the Doppler shift of the light that reaches us. If a certain star were at rest relative to us, we would detect light from it with a certain proper frequency f0. However, if the star is moving either directly away from us or directly towards us, the light we detect has a frequency f that is shifted from f0 by the Doppler effect. The Doppler shift is due only to the radial motion of the star, and the speed we can determine by measuring this Doppler shift is only the radial speed v of the star, that is, only the radial component of the star's velocity relative to us. Suppose a star or any other light source moves away from us with radial speed v, that is low enough so that beta square term in equation can be neglected. Then we have f is equal to f0 into 1 minus beta. Because astronomical measurements involving light are usually done in wavelengths rather than frequencies, let us replace f with c upon lambda and f0 with c upon lambda 0. We then have c upon lambda is equal to c upon lambda 0 into 1 minus beta, or lambda is equal to lambda 0 into 1 minus beta to the power minus 1. Here lambda is a measured wavelength and lambda 0 is the proper wavelength. Because we assume beta is small, we can expand 1 minus beta to the power minus 1 in a power series. Doing so and retaining only the first power of beta, we have lambda is equal to lambda 0 into 1 minus beta, or beta is equal to lambda minus lambda 0 upon lambda 0. Replacing beta with v upon c and lambda minus lambda 0 with delta lambda leads to v is equal to delta lambda upon lambda 0 into c. The difference delta lambda is the wavelength Doppler shift of the light source. This equation is an approximation that can be applied only when V is very less than C. Under that condition, the equation can be applied whether the light source is moving towards or away from us. If it is moving away from us, then lambda is longer than lambda 0. Then delta lambda is positive and the Doppler shift is called a red shift. The term red does not mean the detected light is red or even visible. It merely serves as a memory device because red is at the long wavelength end of the visible spectrum. Thus, lambda is longer than lambda 0. If the light source is moving towards us, then lambda is shorter than lambda 0 and delta lambda is negative, and the Doppler shift is called blue shift. So friends, here we come to the end of our discussion in this lecture, and therefore we sum up. In this lecture, we learnt that the length L0 of an object measured by an observer in an inertial reference frame in which the object is at rest is called its proper length. Observers in frames moving relative to that frame and parallel to the length will measure a shorter length. The Lorentz transformation equations relate the space-time coordinates of a single event as seen by observers in two inertial frames S and S prime, where S prime is moving relative to S with velocity v in the positive x and x prime direction. The motion results in a decrease in the detected frequency and an increase in the wavelength called redshift. So that is it for today. In the next lecture, we shall be talking more about relativity. Thank you very much.